Today, I'd like to extend the idea of a tangent line to that of a tangent plane. Given a surface and a point on the surface, I'd like to find the plane that the surface most strongly resembles. In order to get going on this, we're going to have to review both the idea of a plane and the idea of a straight line, since we will also get the idea of a normal line out of this as well. In order to know the equation of a plane, I need to know a point of the plane, and I need to know a normal vector, a vector that is at right angles to the plane. The idea is, if I take any other point of the plane and form the vector between the 2 points of the plane, it must be at right angles to the normal vector. That is to say, this vector dot product with the normal vector must be 0. This immediately leads to the equation a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. If such an equation is given to you, you can take one look at it, and this number, and that number are the components of a right angle vector. Some people think this looks nicer if you multiply everything out and move all the constants over to the other side, or even write the sum of the constant terms as some other letter, call it d. These formulations all mean exactly the same thing, and in any case, this number, and that one give me my right angle vector. If I'm thinking of a straight line, I have to specify a point on the straight line and somehow tell you the direction along which the linear direction If I'm thinking of a straight line, I have to specify a point on the line and somehow describe the direction of the line also. I'll suppose I have a point P on the line whose coordinates I know, x0, y0, z0, and also I have a vector v whose direction is along the same straight line as the line that I'm interested in. V is parallel to the line. If I were to have another point on the line, the vector that connects the 2 points on the line must be a multiple of this vector v, because that's the direction the line is going in. So the vector with components x minus x0, y minus y0, z minus z0 must be a multiple of vector v. I'll call the name of the number in the multiple t. T is a parameter. By varying t, I can get different x, y, z's on the line. I'll call the components of this v vector a, b, and c. This vector must be t multiplied by vector a, b, c, which has components a times t, b times t, and c times t. Splitting the vector equation into its 3 component equations, we find out that x minus x0 must be a times t, y minus y0 must be b times t, and z minus z0 must be c times t. This is easily rearranged into the usual format. If you're given 3 equations that look like this, you immediately know that these constant terms are the x, y, and z coordinates of a point on the line, and that the coefficients of the parameter t, the a, b, and c, are a vector that points along the direction of the line. Now, I want to imagine that I have some surface, and I'm describing it by some equation, g of x, y, and z equals a constant. We can always achieve such a thing by subtracting one side of an equation from another. I'm going to imagine I have a point P on this surface, and what I'm going to do is I'm going to take my pen and draw a pathway that lies completely within the surface that passes through point P. The points on that pathway are given as x of t, y of t, z of t, and at some particular t value, we are located at point P. At any point of the surface, g of x, y, and z is this constant c, so in particular, this is true for points that lie on this path that I've drawn on the surface. If I stay on that pathway, g depends on x, y, and z, but x depends on t, so does y, so does z. I can write out the chain rule for the rate of change of the g value as I change position along the curve. But on the other hand, since g is a constant, its rate of change is 0. Thinking as I was the other day when we started talking about the chain rule, I can think of this as a dot product. Now, in the rest of my talking today, I'm going to assume that the path is smooth, so its derivative, dx dt, dy dt, dz dt, makes sense for the points that I'm interested in and is never 0 for those points. This is the velocity vector. It's a tangent vector. This is the partial derivatives of g with respect to x, y, and z for components evaluated at the point. I'm going to assume that this vector isn't 0. This says that this vector is at right angles to the tangential direction at point P. But I didn't say anything special about what path that I drew in on my surface, so I could draw another one in. This vector at P is going to be at right angles to this tangential direction also. In fact, under the assumptions that we've stated, this vector of partial derivatives of g is going to be at right angles to every tangential direction at point P. This vector, which we'll give a fancy name to in a moment, if it's not 0, it sticks up at right angles out of the surface. So to summarize, presuming that the path that I draw is smooth, assuming that the gradient of g isn't 0, then I'm going to define the tangent plane at point P to be this plane. The plane is going to contain point P of the surface, and the right angle direction is going to be gradient of g evaluated at this point P. As an example of this, let's think about the sphere x squared plus y squared plus z squared equals 30. You can check the point with x equal 2, y equal 1, z equal 5 is a point of that sphere. Locally, close to point P, the surface resembles a plane. I'd like to figure out what that plane is. All I need to know is a point of the plane, which I know, and a right angle direction for the plane, which we'll figure out. At general points of the surface, the gradient of g is the vector with components 2x, 2y, and 2z. At point P in particular, I know that x is 2, y is 1, and z is 5. This vector is at right angles to the surface at the point P. In view of the previous discussion, the equation of the plane is 4 multiplied by x minus the x-coordinate of the point that we know, plus 2 times y minus the y-coordinate of the known point, plus 10 times z minus the z-coordinate of point P. This is the tangent plane to this sphere at point P. As an example of the normal line calculation, let's think about the surface z equals x squared minus y squared, which is our old friend the saddle surface. At the point on that surface where x is 2, y is 1, and z equals 3, I want to find the straight line that cuts through the surface at right angles at that point. Since this isn't in the right format, subtract z from both sides, rewrite the equation as x squared minus y squared minus z is 0. This is of the type a function of x, y, and z equals a constant. The gradient of g is easy enough to calculate. Partial of g with respect to x is 2x. Partial of g with respect to y is negative 2y. And partial of g with respect to z is the constant negative 1. If we put the coordinates of point P into the gradient of g, we get the desired direction for our normal line. It comes up the vector 4i minus 2j minus 1k. In view of our preceding comments, we can just write the equations for the normal line down. In x, y, and z, the constant terms are just the x, y, and z coordinates of a known point, p in this case. The coefficients of t, the 4, negative 2, and negative 1, are the components of the vector that the straight line is parallel to. Observe, you could also write this as a vector-valued function if that were more convenient. Hopefully, this is enough to get across the idea of tangent plane and normal line. I'm going to make this shorter than usual because I'm developing a cough, and hopefully, though, I don't have the plague or anything.